So we are very pleased to have Professor Phil Hopkins, a professor of theoretical astrophysics and also the executive officer, which is equivalent to department chair for astronomy at Caltech. Phil is an extremely prolific and award-winning scientist, being recognized as one of the top highly cited researchers by Clarivate, and also having won the Warner Prize from AAS in 2016. And just to briefly summarize the academic path that Phil followed, he received his bachelor's in astronomy from Princeton, then PhD in astronomy from Harvard. Then he moved on to Berkeley as the Miller and Einstein Fellow. And since 2013, he's been at Caltech as a faculty member. And I had a very good fortune to overlap with Phil, both at Berkeley and at Caltech. So Phil is probably best known for his theoretical and numerical work in galactic and extragalactic studies. And he often shows these images kind of similar to what you're seeing now, although this is a very pretty animation. These images of galaxies that look completely like real data, but are actually just from his own amazing suite of numerical simulations from his prior collaboration. But Phil's interests are extremely broad, and it ranges from galaxies to black holes to stars and now to planets. And today he's going to tell us about dust gas dynamics, a physical process that is quite universal in astrophysics. So without further ado, please take it away.
All right. Thank you, Eve, so much, and for that very kind introduction. And thank you all for having me. It's been a flurry of meetings, and I hope there's more chances to talk to everybody. Feel free to get in touch if there's things you'd like to talk about, or follow up on some of our conversations for those I did get to talk to. It's really been great, and look forward to hopefully visiting in person someday in the future as well. As Eve said, I'm just going to talk about a subset of some of the work we've been doing. We've had the good fortune to have a big group of fantastic students and postdocs here at Caltech, and that's how I've been able to work on so many different subjects. So I won't get to talk about a lot of the fun galaxy or star formation work we've been doing. I'll only briefly touch on some of the things like cosmic rays that we've been thinking about. But I wanted to talk about something that has been particularly interesting in the last couple of years that grew almost out of an aside of some work we were doing, but turns out to, as Eve alluded to, have relevance across a tremendous range of astrophysical problems and even terrestrial problems potentially. And that's how dust behaves in other fluids. So let me get into that a little more and start by asking, what do I mean when I say dust? I was told, to expect a broad audience. So let me introduce the problem first by saying, what do I mean as an astronomer when I say dust? Well, dust, when we talk about it in astrophysics, is little grains or solids. And composition-wise, we typically talk about either carbonaceous grains that might be graphite or polycyclic aromatic hydrocarbons, or silicate grains that might be olivine, pyroxene, silicon carbide, etc. Don't worry, this isn't going to be a chemistry talk. I promise that's the last chemistry I'll throw at you. But they're solids. They're relatively dense, but their density of order a gram per cubic centimeter, like rocks or what have you. And what are their sizes? Well, in the more diffuse interstellar, circumgalactic, intergalactic medium, we talk about sizes ranging from basically big molecules, a few nanometers, all the way up to micron sizes. But they can get much bigger in dense environments like protostellar and protoplanetary disks. We talk about sizes up to millimeters and centimeters, eventually transitioning to things like pebbles and rocks and proper planetesimals. But they're really important in many ways. And one of the most obvious ways that they're important is that they contain most of the heavy elements in the interstellar medium. In galaxies, in these disks, etc., most of the heavy elements, everything heavier than hydrogen and helium, is locked up in these dust grains. So they're tremendously important if you care about, the origin of heavy elements, of planets, of enrichment, but they also can do lots of things. That also means that they're not by any means a negligible component of even the total budget of things. Certainly if you care about the heavy elements, they're most of it. But even by total mass, there's something like 1% of all the gas mass, which might sound small, but I'll show that is far from being a trace component. It's a pretty significant part of the total inertia of the system. It also means that they're ubiquitous. They're observed in almost every astrophysical environment where we could observe them, and many where we thought we wouldn't be able to observe them or where we thought they shouldn't exist, they've been seen. So they're more ubiquitous than we think they should be, if anything. But by number, they're rare because they lock this mass into, particles of potentially even macroscopic sizes. The number of grains per hydrogen atom is tiny. I have here something like 10 to the minus 12 dust grains per hydrogen atom. And that has some important consequences from a physics point of view. So one is that dust grains are effectively, on most scales, collisionless. And I say here with themselves, meaning that dust-dust collisions are very rare, except in very special environments. So we can treat them like a collisionless system or a group of particles. But they're not collisionless with the gas, meaning that dust-gas interactions can be strong. So at least the large dust grains move aerodynamically, basically. They feel some drag forces, and I'll come back to that in a minute. They're also charged. So a charge to mass ratio in dimensionless units of electron charge to proton mass might be something like 10 to the minus 8. There's actually a tremendously large range of these. The number isn't important here, but what's important is that for the charge they have, they interact very strongly with magnetic fields, and magnetic fields are also ubiquitous in astrophysics. So there's your dust background info dump for those of you not familiar with astrophysical dust. So why do we care? Well, in addition to containing most of the metals, they're hugely important for just a tremendous range of astrophysical phenomena. So these are images, by the way, of galaxies and nebulae within galaxies that are forming stars, where all the dark brown reddish colors are dust that's obscuring light and re-emitting light in the infrared. So they play a huge role modifying the visible spectrum. They interact incredibly strongly with radiation. It's also worth noting that the dust interacts vastly more strongly with radiation fields where it's present than the gas does. Hydrogen and helium, they're kind of boring radiatively. They only have a couple of interesting states, whereas dust grains can interact with radiation at effectively every conceivable wavelength, and they dominate usually that interaction. As a result, they're also tremendously important for things like astrochemistry and radiative cooling of astrophysical fluids, how astrophysical fluids lose or gain energy. They play a central role in planet formation. They're the building blocks of planets. They're one of the central ways, and I'll come back to this, that we think things like stellar winds and galactic outflows are actually launched is through dust dynamics. So they play a lot of different roles, but there's also a lot of puzzles, and I don't have time to go into detail on these. I just want to set up some motivation. There's many decades old questions that haven't been solved in understanding astrophysical dust and its dynamics. So for example, if you actually take a census of astrophysical dust and asked how much metals it contains, it seems to contain more metals than actually exist. So there's something wrong with the budgets we have or with how we're characterizing the dust grains. There's also an observation that keeps recurring where when we look in our solar system, either at micrometeorite impacts that we can measure from the ground or space probes that collect interstellar dust grains that hit them, there's too many very large grains, and the too many is actually too many in a sense that these can't exist everywhere in the interstellar medium, or we would see them and they would violate other constraints we have, but they seem to be hitting Earth. So where are these coming from? We've also seen persistently that dust forms much too early in the history of the universe compared to our models for how these grains should form in the first place. It's present at incredibly early times. This is one of those examples I said where we see it where we don't think it's supposed to be. There's also, as we've made beautifully detailed measurements of things like the cosmic microwave background, where if you're a cosmologist, dust is one of those terrible things that is just in the foreground messing up your observations, and you have to subtract it. People realize that the dust polarization and how it aligns with magnetic fields isn't how we thought it would. It's basically aligning at the wrong angles with respect to magnetic fields than we thought naively in theory that it should. And it does a lot of other non-intuitive things. Again, I'll touch on some of these in more detail. I just want to give you a flavor of some of the astrophysics problems that have persistently been around for decades. So what I'm going to argue is that a lot of the problems in our understanding of dust stem from a common astrophysical assumption that is very wrong, and everybody knows it's wrong, but I think we only are just beginning to appreciate how wrong it actually is. And that's to assume that the dust acts like the gas, basically. So a very common astrophysical assumption, with the exception of a couple subfields like planetesimal formation, is that you say, well, I can estimate order of magnitude the gyro radius or the drag deceleration length of a dust grain. And it's much smaller than a lot of the macro scales I care about for astrophysical systems. So to first order, I can treat the dust grains as a passive scalar that are just being advected along with the gas. They're just carried along for the ride. And that's wrong. And it's not just wrong at the level of some perturbative expansion in the ratio of scale lengths. It can be orders of magnitude wrong on every scale, basically. So why is that wrong? The length scale calculation is fine. Well, I'll go into a lot more detail on this in the next few slides, but we've known that even if the length scales are small, this is a bad assumption for a long time, even from terrestrial experiments, basically. So for example, these are the results of some numerical experiments and also actual lab experiments in terrestrial turbulence. So people have studied in terrestrial turbulence how particulates, like dust grains or other particulates, cluster. Even for passive scalar particulates, just passive particulates, meaning that they don't push back appreciably on the gas. If you embed them in a turbulent, incompressible fluid, how do they mix? And these simulations that are showing here, the black dots are the particulate or the dust grains, and the colors represent the vorticity fields of the gas. And you can see that they don't just move with the gas. They cluster very strongly with respect to the vorticity and strain fields in the gas. And this actually has a lot of literature on it on Earth, mainly because of industrial applications. This is actually quite relevant for a lot of industrial applications, and there's a interesting experimental literature. But I'm an astronomer, so I think that terrestrial fluid is boring, basically. Apologies to my colleagues here who care about terrestrial fluid dynamics, but terrestrial turbulence, it's subsonic, it's not magnetized, it's not doing any of the really wild things that astrophysical turbulence can do. And that actually makes a difference for the dynamics of the dust grains. So a lot of what I'm going to talk about for the rest of this talk centers on a family of instabilities that a postdoc at the time, John O'Squire, who's now a professor at Otago in New Zealand, and I sort of encountered by chance when we were looking at this problem. We were wondering about, how dust grains move in astrophysics. And I sort of suggested that Jono look at a very toy version of a problem where you were trying to push gaseous fluid with a wall of dust. And I suspected this would be unstable to maybe some kind of Rayleigh-Taylor-like instability. And Jono basically did a calculation, found that it was unstable, but said, I think I can do the magnetized version of this problem. I said, okay, cool, let's look at that. And that was unstable too. And then he said, let me add this layer of complexity to the problem. And then he proposed that he could do a derivation that would show that basically any coupled dust gas system anywhere in the universe was unstable, even without knowing the form of the forces on that system. And my response to him was, this doesn't make sense. How can you possibly do that? But what's really cool is that you can, in fact, and Jono deserves 100% of the credit. And you can see this paper if you want to see the details. It's very mathematical derivation. I had to learn, frankly, some new math to follow the proof, but It's very cool. You can show that as long as certain very general properties are true, a dust gas fluid is always unstable. So let me give you the cartoon version of this. So you have dust grains. They're moving according to some equation of motion, like I've written down here. And let's say incredibly generally, that equation of motion looks like this. It's got some coupling tensor that depends on the velocity difference between the dust grains and the gas, and some arbitrary set of other acceleration terms. I don't care what those are, basically. This coupling term can be an arbitrary operator. It has to obey some certain mathematical properties, but those are incredibly general. But what about this dependence on the gas? Well, it can be a lot of things that we know are there. So any aerodynamic drag, whether it's Epstein drag or Stokes drag, Coulomb interactions with the surrounding medium, Lorentz forces, charge exchange, they all obey this general functional form. So for example, drag forces, aerodynamic drag, you have a dust grain moving through a sea of atoms or molecules or ions, it'll just feel some drag force that depends on its velocity with respect to the fluid, where this drag constant, in different fields, you give it different names. In astrophysics, this is often called the stopping time, this coefficient. It's the time scale it would take to decelerate under drag, just from collisional drag, for example. But Lorentz forces also follow this, right? I said dust grains are charged. They feel Lorentz forces. So they're guaranteed to have this coupling to the gas, where generically you have a function of this form as long as you have finite charge, basically. So you have this coupling term. Your gas equations can be anything you want, but they have to include the dust back reaction. What do I mean by dust back reaction? Just equal and opposite force. If the gas is exerting a force on the dust has to exert an equal and opposite force on the gas. So that's trivially defined by reference to whatever force the gas exerts on the dust. And then the last piece that needs to be present is that there must be some difference in the forces that are acting on the dust grains versus on the gas. And what any force difference will give is some drift or slip velocity. Basically, the velocities of the dust as it's being pushed on by external forces, and the gas as it's being pushed on by its forces will not be exactly equal. You can think of this in the classic example of aerodynamics. This is just the terminal velocity is the drift velocity of, in this case here, parachuter as they're falling, right, with a force of gravity and a drag force on them. But this differential force can come from a huge variety of things. The gas feels pressure forces, the dust doesn't. The dust, I already said, interacts more strongly with radiation. So if it's absorbing photons, those photons will push the dust grains and give it a non-zero drift velocity. It's almost impossible to contrive an astrophysical situation where this drift velocity is zero, basically. So that's the necessary condition. And what's really remarkable then is that Jono showed that as long as you meet those conditions, this mixture of dust and gas will always be linearly unstable. And in fact, it will be linearly unstable to an infinitely large family of instabilities, where if you imagine that you could take that system and consider the dust alone or the gas alone, the dust alone would have its own set of modes or behaviors, things like drift or Lorentz motion, gyro motion. The gas alone might have its own set of modes or behaviors like, sound waves or shocks or Alphane waves, that kind of thing. And one of the fun things about this instability is it turns out that if you take any mode out of the gas column and any mode out of the dust column and pair them up, they generate a new instability, and every pair is different. So that's saying a lot. Let me actually give you some examples of this along the way. So the simplest case we could think of is what we called the acoustic resonant drag instability. We called this whole family the resonant drag instabilities. So what is the acoustic resonant drag instability? It's the interaction between dust getting drifted or slipping through gas and a sound wave in the gas, basically. And this is a diagram. Basically, the wave, a sound wave has some pressure perturbation. The pressure perturbation means that there's a differential in the velocity field that's pushing on the dust. The dust gets pushed in a way that amplifies the pressure maxima of this system. And again, you can see this paper if you want a more detailed physical explanation of how this instability operates. But you can think of it as the dust front basically pushes on the sound wave front and steepens the sound wave as they're both moving together. Now, there's a resonance where this instability has a maximized growth rate. And that resonance comes when basically you line up the motions I was just describing of the sort of sound wave front and the motion of the dust. So what do I mean by line up? Imagine that the dust is getting pushed through the gas. It's got some drift or slip velocity in some arbitrary vector direction. This cartoon I drew here. Now imagine I superimpose a sound wave on it. Sound wave, I've got my peaks and troughs here with some k vector pointing in this arbitrary direction. The sound wave has some phase velocity that's just the sound speed along its vector direction. I've picked a relative direction of the sound wave and the drift velocity so that the drift velocity along the direction of the sound wave is exactly equal to the phase velocity of the wave. That's where this resonance will occur. That's basically where what I just described will sync up. You can think of it as basically everything's adding coherently because the velocities are synced up or the frequencies are synced up along the direction of motion, basically. So what this means is that different instability modes will have a sort of preferred direction. And you can see this, again, I don't want to spend too much time on the technical details in this plot of the growth rate of this instability versus the angle. Here we call it the mode angle. This is just the angle between the direction in which the dust is drifting and the sound wave that it's sort of interacting with. And you can see these different curves correspond to different assumptions, but you can see this resonance where you have this lineup of the angles so that they push on each other. This is the maximum growth rate of the instability. It formally goes to infinity, actually, right at the resonance. So that's why we called it a resonant instability, basically. So that's analytic theory. What does it look like when you actually try and model this going nonlinear? So with an undergrad at the time, Eric Mosley, who's now a grad student at Princeton, we tried to do some numerical simulations of this very simple instability. We just took a periodic box of uniform density gas and a single identical species of dust grain. There's no magnetic fields yet in these simulations. And all we do is we subject the dust grains to some external force. You can imagine that it's maybe some radiation they're absorbing that pushes them through the box. And these are just two projections of the box. On the left, the drift of the dust goes up, and on the right, you're looking at the same box with the drift coming at you. And the colors are the gas density field, and the black points you'll see in a second, which are initially uniformly distributed, are the dust grains. So we let this go, and very quickly you see that the dust starts to form structure, and it'll get nonlinear in a moment. It starts forming these crisscross patterns. That's actually the resonant angles appearing visually. And then it breaks up into these sort of constantly churning vortex structures, basically, and clumps and filaments along the line of sight. So we now have, sort of order of magnitude fluctuations in the local amount of dust in some patch of the system, in the simplest case we could possibly think of. So you can keep adding complexity to this. An important one is, of course, adding magnetic fields and charge, because I said dust grains are charged, magnetic fields are everywhere in astrophysics. But remember, I said sort of every pair of gas modes and dust modes generates new instabilities. So already this explodes the number of instabilities that actually exist. So for example, the dust can have drift motion, but it also has gyro motion. Even if the dust isn't drifting, it'll be doing gyro orbits around the magnetic fields. The gas now has, instead of just a sound wave, you got fast and slow magnetosonic waves and Alphane waves, and every pair of these generates a different instability. Basically, you can think of there's an interaction between dust gyro motion and fast magnetosonic waves. There's an interaction between dust gyro motion and Alphane waves. And every one of those generates a different instability with different resonances that behaves a little bit differently. And the resonance structure now gets wildly complicated. It's, great fun if you're a certain type of theorist and terrifying otherwise, but this is just an example of a map of the resonances for even a specific case where each of these lines corresponds to a different resonance between all these different modes. This is between two angles, because now you've got a magnetic field to introduce another angle. And this is even just a slice through that diagram. So now there's resonances all over the place, which is actually quite important because now it means there's resonances all over everywhere. There's tons of different ways these instabilities can grow. I won't spend much time on this slide. This is just to make an important point that, first of all, you can show mathematically that the resonances will always exist. There are no conditions where there won't be a resonance, basically, for a magnetized fluid with charged dust. And the growth rate of the instabilities formally increases without limit to short wavelengths. So the growth rate becomes formally infinite as you go to infinitely high wave number. There may be effects that cut that off. I'll just mention those incredibly briefly, but and some of these really do have some very interesting behaviors. So for example, there's an Alphane wave resonance where, for example, I just said you might cut off these effects, kind of like Alphane waves themselves. So this is a cartoon visualization of something on gyro orbits moving through an Alphane wave, kind of represents what the dust might be doing. But I won't spend too much time on this, but for people who care about magnetized plasmas, like an Alphane wave, this interaction, this sort of beat interaction instability between dust and magnetized gas is not damped on any scale by viscosity or conductivity. In fact, you can show that this instability is unstable at least down to the ion gyro radii in the plasma. And probably, we've done some kinetic MHD calculations, it's probably unstable down to the electron gyro radii. So there's an incredibly large range of scales that this instability would operate over. Sorry, that's just part of the cartoon. There's also various gyro instabilities that involve different types of interactions that have growth rates that peak at certain frequencies or wave numbers, basically. There's also a different family of instabilities that appears for people who like cosmic rays, and I'll come at the end of the talk just briefly mentioning some cosmic ray stuff, that are actually directly analogous to known instabilities of cosmic rays that have been, in some cases, known for decades. So there's an instability that, as we were characterizing it, we realized was just the dust analog of there's both an analog of what people call the gyro-resonant cosmic ray instability and the non-resonant or Bell instability of cosmic rays. These are instabilities as a population of cosmic rays moves down a magnetic field line that generate magnetic field fluctuations in magnetized plasma with cosmic rays. And we realized this analogy, and in fact, you can push it further and actually show that the cosmic ray instability is technically is an example of a generalized case of these resonant drag instabilities. It fits into the mathematical framework above, but it also provides a neat way of thinking about dust, which is, if you're more familiar with high energy astrophysics, you can actually just think of dust grains as very heavy, non-relativistic cosmic rays. And a surprising amount of that intuition carries over. But really, these things just pop up everywhere. And this is a cartoon just showing a bunch of different situations in astrophysics: active galactic nuclei, H2 regions, molecular clouds, the solar corona, the circumgalactic medium, the warm interstellar medium, planetary disks, and just trying to make a little cartoon of which of these instabilities might be the fastest growing in these different regimes. But the really important point is that they're present in all of them. So with that in mind, we wanted to actually go a little further in the last year or two and ask, what do they do in these different regimes? So this all happened starting in sort of mid-2017. And we wanted to explore what was going on in more realistic environments. I see there's a question in the chat. Sorry, I missed that earlier. The chat asks, what fraction of the dust did you assume in your simulation relative to gas? And do the thermodynamic parameters of the system affect the strength of the acoustic resonance instability? Good question. For the former, for what fraction? We assumed about 1% of the mass was in dust. The growth rate of the instability basically scales with some power of that. So where the power is between to the sort of 1/3 and 2/3 power, depending on which instability you're looking at. So it's always some sublinear power of the metallicity or of the dust to gas ratio. And the thermodynamic parameters do affect the strength of these resonances and the growth rates of the instabilities. You can sort of come up with a couple key parameters that drive it, like some dimensionless ratio of the drag time scale of the dust or the gyro time scale of the dust to other characteristic thermodynamic timescales of the system, basically. And those all enter in some powers to the growth rates. Happy to talk more in detail. It depends, of course, on which of these instabilities you're talking about. But good question. So let me jump into, for the rest of this talk, giving some examples. In the last 2 years, we've sort of embarked on a program of exploring how these instabilities might manifest in more realistic astrophysical settings. So one example we wanted to look at was dusty outflows in molecular clouds and H2 regions. So here the idea is, again, for those not familiar, you have a massive star that is emitting a tremendous amount of radiation that is being absorbed primarily by dust grains in the region around it. And that radiation is imparting enough momentum, just the photon momentum, just L over C, is more than enough to accelerate the bulk of the dust and gas away from the star and push it away from the star. But what we've usually assumed in the past when we model this is that that radiation is instantly and perfectly transferred from that momentum, sorry, the dust absorbs the photons. We've usually assumed in the past that that momentum is instantly and perfectly transferred from the dust to the gas and everything just moves out together. But I just argued that that's not a stable configuration. And in fact, trying to push the gas with the dust will be unstable. So what does that actually look like? So we set up some numerical simulations motivated by this kind of setup to see what that would do. We wanted to simulate it. So you can imagine setting up some box where you have a radiation flux or force that's coming up from the bottom of your box, hitting dust grains and being absorbed by dust and pushing them. And then the dust itself couples to the gas through some combination of Lorentz forces and aerodynamic collisions and drag, basically. So there's already, even though these are idealized, a fair mess of physics happening in these simulations. So what does this look like? So this is a zoom in of a patch of this region. This is like simulating a little microscale patch. And this is from Daryl Seligman's work in the paper on the previous slide and in this paper, where now we're looking at a little patch of the gas, and you can see this acceleration direction labeled. The dust will start to line up into sort of filaments along the acceleration direction. And I've also labeled the dust by color. This accounts for the fact in this simulation that there's not one size of dust grain. There's a spectrum of dust grain sizes, and different size dust grains have different charge and different aerodynamic drag coefficients because it depends on their area, how collisional they are. And you can see that actually you get separation even between different sizes of dust grains. You get the red or the large grains getting launched most strongly in the acceleration direction, while the small grains kind of lag behind, and they form almost separate channels. So this is zooming in on a micro scale of this simulation. Let's zoom back out on a macro scale. And we actually ran a series of sort of boxes of different scales, and that's what's shown in this little tower. I don't know if you can see my mouse, can you? Cursor?
Yes.
Okay, thanks. So starting from some very tiny scale in this box, you simulate a larger box where effectively one resolution element of this big box is this entire small box here. And you can keep going up in the hierarchy and eventually simulate a large column. This is an elongated box here, but each of these is kind of embedded in these larger regions, basically. And the dynamic range of scales here is a factor of 1 million or so in linear dimension. And that's only still a subset of the full dynamic range of these instabilities, but at some point we got to the limit of what we could even with these box-in-box type methods simulate. But on all scales, you can see this generating structure. Basically here, the brown and black are the dust grains, where the color represents different dust sizes, and the bluish colors are the gas density field. This is just a quantitative plot showing as a function of scale height in this long box, how the dust clumping factor, how strongly the dust is concentrated, fluctuates along this medium. And you can get factors of hundreds or thousands clumping factor of the dust. And these are just some beautiful visual images of what this looks like in these particular simulations. The names aren't important, they're just slightly different parameter choices for the simulation. But you see the elongation, the direction of elongation is the direction that this is all being accelerated out. So this is still launching some kind of outflow, but you see this incredible amount of dust structure in these systems that I also just think is visually great to look at, but you can also see some slight differences here. These are a somewhat different set of parameters, and visually they are different in both the dust morphology and the color scale. These are closer to what you might find in an H2 region as compared to a more neutral region of a molecular cloud. And that's through those thermodynamic properties modifying which instabilities are dominant, basically. But they all form a tremendous amount of small scale structure in the dust. And people who are used to looking at images of molecular clouds will probably find a lot of these dust structures incredibly familiar. We see dust morphological structures like this on similar scales to what these simulations are trying to represent. But this is really dependent on doing this dust dynamics properly. So these are some examples of simulations where I've taken the exact same initial conditions and physics, but turned off some key pieces of the physics and let them develop until they launch the grains out and or lift the grains up to some height. And it's not important exactly what the labels are here. Here's the important thing. These two left panels assume this super naive model that the dust is simply advected with the gas. We're not doing dust dynamics in those panels. We're assuming the dust gets pushed with the gas. So this is still a non-trivial simulation. This is a radiation hydrodynamic simulation of a constant radiation flux trying to launch a wind. But you can see the simulations look real boring, basically. It just smoothly accelerates this material out. And this is what most of the previous astrophysical work has assumed on this subject, basically. And you just don't see any of this structure. The middle panel allows the dust dynamics to actually be evolved and solved, but it ignores the Lorentz forces on the dust grains. You can imagine it's as if we just said the dust grains carry zero charge instead of attempting to calculate their actual charge. So they don't see magnetic fields. And you can see it develops structure, but it's totally different structure. It's much less structured. There's almost no small scale structure. There's some sort of broad angle contour, and that it turns out this angle that you see here, this macroscopic angle is exactly the resonance angle. And the reason you can see it is because it turns out if you turn off the Lorentz forces for this idealized problem, there's one dominant resonance that dominates, and that's the resonant angle that you see. And then these two panels on the right use different methods to treat the radiation, but they both critically integrate the actual Lorentz forces and dust drag forces. You can see those break up into this incredible amount of structure, basically. The difference between them is much smaller than the difference when you ignore the dust dynamics, basically. So it's really crucial, it seems, to account for this. And we're now trying to make some quantitative comparisons. I mentioned, these might look familiar if you're used to looking at real filamentary structures of dust. Folks like Eve will know that filaments has been the buzzword in studies of dust in molecular clouds and H2 regions for the last few years, where we see these kinds of structures. And on the right are sort of real images, and on the left are some of these mock images. You even see like fun little horsehead nebulae type things that form automatically. And we're also looking at how this affects things like observed extinction curves. I don't have time to go through this plot in detail, but remember I said that different size grains can be affected differently. Well, if you have a different relative distribution of numbers of small versus large dust grains along a line of sight, it'll actually modify how light propagating through that sight line is extincted. Basically, small grains are more efficient at attenuating short wavelengths of light. And so the relative amount of attenuation at different wavelengths will be modified. And so there's really quantitative predictions that you can make from this now to compare to observations that are distinct from the host of other hydrodynamic and magnetohydrodynamic instabilities that are present. I mean, you might say, this is cool, but instabilities are everywhere. There's hydrodynamic and MHD instabilities in these systems already. You know, what does adding one more instability to the pile do? But actually, it's really important. Not only did I just sort of show you an example where it totally changes the morphology, but there's things that these RDIs can do that things like a Kelvin-Helmholtz instability can't do, like segregate grains differently based on their sizes. A KH instability doesn't know about the grain size and doesn't do that, basically. So there are qualitatively distinct phenomena that emerge from these than from other known MHD instabilities. There's a lot of other examples that we have that we're trying to apply this to, and I'll mention these a little more briefly because it's a little more early stage work. Uli Steinwandel, who's now a postdoc at the CCA, has been doing simulations and exploring the implications of this for dust in cool star atmospheres. So we know that cool stars like red giants form dust in their atmospheres, and actually that increase in the opacity from the dust as it forms in the stellar atmosphere can cause it to absorb more of the stellar radiation and launch outflows from it. But again, these instabilities haven't really been appreciated in that context. Despite a tremendous amount of work in the dust there, they haven't been recognized. Although I should be fair and note that in the process of looking at this, we did find one paper from 1994, I think, by Nuclei et al. That actually we realized did almost all of Jono's derivation to find these resonant drag instabilities. And then unfortunately, in the last sort of page of the derivation, they said, well, this is getting pretty messy, so we're going to assume spherical symmetry and a couple other assumptions to simplify the math, which actually eliminates all of the instabilities. They'd basically gotten like one line away from deriving it all. So we almost got scooped by 2.5 decades, but you know, there's a lot to do here. And I think this has appeared in simulations, even in this field, without people fully realizing necessarily what was happening. But Uli wanted to look at a more idealized case of what this would do to variability in these outflows. So he's run simulations that zoom in on different scales and correspond to patches of this wind and what the dust would be doing on different time scales as it varies on microscales. And you basically get variability in human time scales. So on the larger scales of order 100 solar radii that represent the size of the base of these outflows, you get time scales of order year for variability. But microscale patches can be varying on 1 minute time scales even. And that can do cool things to actual observables. So the paper he has in preparation shows things like Mach light curves showing the magnitude change of the stars owing to dust in the outflows for both AGB type simulations where we're modeling an AGB outflow in the dust in there, or R-core-Bohr or CB type stars, which are the result of systems that expel a very large quantity of dust. And we're looking at the variation in those dust expulsion episodes where you can have it change by multiple magnitudes in luminosity as these dust clumps form and dissolve along the line of sight. So basically, this is a way to explain some of the variability that we've seen that people haven't been able to account for. And it also, again, changes the shape of things like the extinction curve in these systems. Another student, Nadine Soliman, is now looking at this at Caltech in the context of looking at active galactic nuclei and quasars, where you've got a supermassive black hole accreting, and we know these are surrounded by what we commonly call the dusty torus around them, just some surrounding ambient medium of dust and gas. And again, you have a qualitatively similar situation of the radiation pushing on the dust and gas and generating these instabilities. The key parameter that makes this different from the cases that I discussed earlier is basically that the infrared and Compton optical depths in these systems are extremely high, reaching up to thousands. And again, that doesn't eliminate these instabilities, but it changes which instabilities are the dominant ones and which resonances are the dominant ones. So we're exploring with Nadine what that will mean for observed sort of variability in sightlines to quasars and whether it can explain some of the phenomenology. So this is sort of a cartoon of just pasting one of those previous simulations as a cartoon of what we might imagine seeing as this sightline goes through this clumpy dust. You'll see time variability in ways that are distinct from other types of time variability. And in particular, there's a couple classes of variable AGN that we think this might be able to explain that thus far there's basically no good explanation for, where we see certain types of variation in the dust between us and the AGN. So again, there's a host of examples where we could think about applications with wildly different time and spatial scales. Even going down to things like coronal dust and zodiacal dust in our solar system, where in some cases, some of these instabilities are operating on sort of 1 second time scales, basically, all the way to things on galactic and circumgalactic scales that are operating on 100 million year time scales, basically. But one last thing I want to mention, I'm just going to very briefly touch on 2 more applications that are interesting. And this is just to give you a flavor of them. I don't have time to go in detail. One is going to the one place in astrophysics where there has been a lot of work on looking at dust dynamics, which is planet formation. So from the perspective of these instabilities, what do I need to do if I want to consider a planetary disk? Well, I should add rotation, in particular centrifugal and Coriolis forces. And it turns out that there, the dominant resonant drag instability is a resonance between the epicyclic motions and the dust drift motions that we were calling for a moment the epicyclic drag resonant, epicyclic drift resonant drag instability, very awkward name. And then we realized as we were working on this that this was in fact a known instability that had generated a tremendous amount of work in the planet formation field. It's what's called the streaming instability that was discovered by Uden and Goodman in 2005. And there's a whole industry of people simulating the streaming instability of dust grains. So again, not all of these instabilities were new. What was new was really the discovery that there's this family that links all these different systems together. And this is just one example of a simulation, not by us, by Kowalik et al. 2013, of the streaming instability in a planetary disk. So you're looking at the dust distribution in some plane that represents the radial and vertical direction of the gas, and you see the dust clump up, kind of similar to some of the previous simulations, but distinct in many ways. And many people have focused on this as a way to aggregate dust grains in a planetary disk and potentially form planets as well. I don't have time to talk about this in detail, but basically the idea here is that there's a decades-old problem in planet formation of how you get bigger than something like a millimeter or a centimeter without the dust grains just bouncing off of each other or shattering or spiraling in and getting swallowed by the star until they're big enough to actually form a proper planetesimal. This is often called the meter gap, but as Eve and many others will tell you, it's actually more like a millimeter through 100-kilometer gap where there's a problem understanding this. And one of the ideas is that these instabilities could aggregate dust grains and cause them to clump together into such large concentrations that gravity would actually pull them all the way together into a planetesimal from centimeter or millimeter sizes. There's also applications in atmospheres and terrestrial systems. So if you model this in a stratified buoyant medium, aka a planetary atmosphere, you get resonances with Brunt-Väisälä or buoyancy modes. And it turns out there's actually a fun analogy where I'm just going to skip this to sort of known instabilities of things like colloidal suspensions. And in fact, we're actually working with a group studying volcanic ash settling, where we think this instability occurs as volcanic ash settles, specifically the sort of Brunt-Väisälä resonance in the atmosphere. But this can actually be very interesting for a lot of atmospheric dynamics calculations. If you want to model atmospheres, this is actually an important parameter, how quickly sediment or dust or particulates actually settle out of an atmosphere under gravity, basically. I'll skip this because I'm running out of time. So the very last thing I wanted to mention, just again, a couple minutes, is the question of how this can all intersect with cosmic rays. I could have easily given a whole talk about cosmic rays, and I actually debated doing so because we've been doing a lot of work in our group on cosmic rays on galactic scales. For those who aren't familiar, again, cosmic rays in astrophysics are relativistic particles. There's a tremendously broad spectrum of them, from sort of mildly relativistic GeV particles to ultra-relativistic particles. And in the local interstellar medium, there's about as much energy in relativistic cosmic rays, most of the energy being in about GeV protons, as there is in other things like thermal energy density, magnetic energy density, radiation energy density. So they're not a negligible component of the interstellar medium. We think they come from things like supernova shocks or AGN jets, but I'm not going to focus on that. But they propagate through the interstellar medium by, they're charged, of course, so they're on Lorentz orbits, and their gyro radii are very small compared to macro scales in the interstellar medium. So for example, in the diffuse interstellar medium, a typical gyro radius of a 1 GeV cosmic ray, where most of the energy is, might be 1/10 of an AU, very small compared to macro scales of the interstellar medium. So they're bound onto the magnetic field lines, and they move along magnetic field lines. And then but they don't just move at C down a magnetic field line. As they do their gyro orbits, if there are fluctuations in the magnetic field on the same spatial scales of order the size of the gyro radius, the cosmic rays effectively scatter off of those fluctuations. You can think of it as it's formerly pitch angle scattering, but really basically the directions of the cosmic rays bounce around. And this is what sets their effective bulk transport properties. What we usually call the diffusion coefficient, or the streaming velocity of the cosmic rays, is ultimately set by the fluctuations in the magnetic field that scatter them around, basically. And these are just some numerical PIC simulations. I showed them earlier, but they're trying to calculate this scattering in a shock here in the first place. And all I'll allude to on the galactic scale is that there's been a flurry of work, a lot of it from our group, but from many other groups as well. Here's a couple of students, TK Chen and Kung-Yi Su, who studied this, on how the propagation of cosmic rays can modify not just interstellar chemistry or more subtle properties, but even macro scale galaxy formation by being an extra source of pressure that modifies the launching of galactic outflows or accretion onto galaxies. And this is a cosmological simulation of a Milky Way mass galaxy, showing the rate at which it was forming stars versus cosmic time, where we explicitly evolve in some of these runs a population of cosmic rays. So in the pink line, we ignore cosmic rays entirely. In the white line, we include cosmic rays, but allow them to propagate very quickly. And that causes them to just escape the galaxy before they do anything, because they're not strongly enough scattered. They don't get confined and build up energy and pressure that can interact with the surrounding medium. The blue line over-confines the cosmic rays. We allow them to propagate too slowly. Why would that cause them to do nothing? Well, then they get trapped in very dense regions of the gas, where they eventually slam into an atomic nucleus and lose all their energy, basically. It all comes out in gamma rays, effectively. The yellow line is the sort of just right Goldilocks zone, whatever you want to call it, where cosmic rays interact somewhere in between and can have a dramatic effect. In this case, they suppress the star formation rate of the galaxy by a factor of 5 or 10. So that's a huge effect. For those who aren't conversant in that literature on the star formation rate of a Milky Way mass galaxy. But you can see the problem is it depends on how fast the cosmic rays are moving, which depends on how quickly they're being scattered by these small scale fluctuations in the interstellar medium, which we don't know, basically. So we can constrain this with Milky Way observations, with solar system observations of cosmic rays. This is just an example of fitting all the Voyager and AMS-2 data to an empirical model from a recent paper of ours, where we just assume a constant scattering rate in space and time, depends on energy of the cosmic rays, but otherwise is fixed in space and time. So we can calibrate this. And interestingly, the calibration that fits the data the best is very close to that sweet spot where the effects are maximized. But the problem is this calibration only constrains the behavior of cosmic rays in the galactic ISM near the sun. So we don't really know what it does elsewhere. And it turns out that the allowed range of models from that calibration is still all over the place. Again, I don't have time for details, but all these different star formation rates are different allowed cosmic ray models, basically. So what's the real answer? Well, the problem is that theory-wise, we don't really have a good understanding of the what's causing the cosmic ray scattering. If I'd given a whole talk on cosmic rays, I would have spent 10, 15 slides on this. As it is, I'm going to spend less than one slide. Basically, all I'm trying to say is that in this slide is that the popular models that have been proposed in the literature don't actually fit the data at the solar system, and there really isn't a good model for what drives this microscale scattering. So if I'm going to close the talk in my last slide by putting a wildly speculative couple of slides, what if the dust does something interesting through these instabilities? That might sound a little wild until you realize there's a really striking coincidence in the interstellar medium, which is that the gyroradii of dust grains and the gyroradii of the cosmic rays that contain most of the cosmic ray energy in the interstellar medium are almost identical. And there's a spectrum of dust grain sizes, of course, and a spectrum of cosmic ray energies and gyroradii, but those gyroradii of both heavily overlap under almost all interstellar medium and circumgalactic medium conditions. And what that means is that they all resonate with each other. There's known instabilities of dust resonating with magnetic fields that I just described to you. There's known instabilities of cosmic rays resonating with magnetic fields that I alluded to earlier. This suggests terrifyingly that if we want to do this problem right, we need to consider the triple resonance of the magnetic fields, the dust, and the cosmic rays all together, because they all interact very strongly around that gyro radius, basically. And with Soching Ji and Jono Square, we actually showed that this can have, depending on the strength of the resonant drag instabilities, this can have the effect of either making the cosmic rays move faster by damping some of these fluctuations, or have the effect of pumping them up and making the cosmic rays move slower. So it's something we've just started to even think about. Wild speculation is that this could be really important for things like the cosmic ray transport, but that's about all I've got to say about it right now. And I'll wrap up there. A lot of this talk was speculation, but I hope I've convinced you that at least we should be thinking in these astrophysical contexts about how dust interacts with the medium around it, and that this could be a lot more important than we've thought in the past. So thank you very much. Happy to answer questions.
All right, thanks, Phil, for the very nice talk. I'll clap for everyone else since we're on Zoom. We see, I received 2 extra questions. So actually, I'll let Mohit ask your question.
Yeah. Hey, Phil, amazing talk. So I have a nice question. You showed that in one of your plots that actually extinction follows neutral hydrogen density. Yeah, but I think one takeaways from your initial discussion, at least for me, was you should expect different spatial evolution. So why it is so in this case?
Yes, that's a good question. So actually in the paper this comes from, which was at an archive a month or so ago, we talked about this a little more quantitatively. And yes, the point was that on large scales, if you look at the second and third images here, the AV is the dust extinction and NH is the hydrogen column density. Those maps look very similar. And so on large scales integrated through a line of sight, there's a pretty good correspondence between dust and gas, which is kind of reassuring because there's a lot of astrophysical evidence that on large scales, the two do trace each other broadly. There is some separation, but it's not a lot. There's sort of factor of 2 fluctuations in the ratio of AV over NH if I impose these maps on each other. But the important thing, what's striking is that if you make a 3-dimensional map, the correspondence is much less good. Basically, what's happening is these are projected quantities, and it turns out that there's very strong separation on small scales, but in the projection, it mostly integrates out, and it actually integrates out a lot faster than like Poisson, which is something I still don't actually fully understand why it sort of converges faster than Poisson in the integral. It's like there's some long-range correlation between the modes, basically, that they're sort of anti-correlated. So yeah, I don't fully have a neat explanation for exactly how quickly it integrates out, but it's clear that, you know, in the projected long scales, they end up mapping to each other. But it's the case that, you know, the strange thing is that, you know, the amount of structure we see here was driven by the dust on microscales separating from the gas, right? Because you don't get these filaments at all in these simulations if you don't allow the dust to separate from the gas. So it seems like it's able to separate and introduce these forces that push this thing towards collapsing into these filaments to first order the filaments, then drag the dust and gas together into the filaments. But they're driven by the small scale separation. Does that sort of answer your question?
No, it's fascinating. I think so. I think last bit of your explanation answers my second part as well. I was also wondering that how turbulence actually affects this process.
Mm-hmm.
So I think you said the scale matters, that small scale, maybe at large scale turbulence.
Mm-hmm.
Yeah.
Yes, no, I think that's right. So, you know, if you realistically had a lot of other stuff churning up the medium here, for example, you'd also have a lot of other sources of turbulence that would potentially modify things. And I think on large scales, those would cause the more dominant large scale motions of a lot of these things. Whereas on small scales, you might be dominated by these instabilities. We looked a little at this in a recent paper that John O'Squire just put out of looking at the difference between a box that was purely driven by the resonant drag instabilities to cause fluctuations versus one where we externally stirred it, basically, but still followed the dust dynamics. And there are some interesting differences. There are structures that can form in the former that can't form in the latter. But it's something that definitely needs more work, basically. Just barely scratched the surface.
All right, and we also have a question from Robert. Robert, did you want to ask questions? Or shall I read it out? So I'll read it out. So Professor Robert Brandenberger asks, in terms of the mathematics of the instability that you showed, is there a connection with the dendritic instability in condensed matter systems like snowflake formation?
Well, I'll confess, I don't know what the dendritic instability is. I apologize. That's probably my ignorance as an astrophysicist. So I don't quite know how to answer the question. I apologize. But I'm happy to, you know, talk offline or read more to find out and learn more about it. We have, as I alluded to a couple of times, we found some surprising connections as we've tried to look for applications where this has actually had connections along the lines you're wondering about with other known instabilities. Oh, thank you. I'll check out that work and see. I'd be very interested to see. Yeah, as I said, we've found out just recently about this sort of colloidal suspension relation, where I think those are mathematically very closely related. And you know, some of these things where they're well studied in other fields, we can hopefully import some of the apparatus folks have used to study those. Excellent. Thank you for the reference. I'll grab that and take a look now.
Other questions? Ronnie?
Thanks for that talk. This question may be ill-posed. When does like how much dust do you actually need for it to sort of really start impacting things at various scales? The reason why I ask, as someone who's interested in reionization, you start out with a universe that has little dust, there's a transition, and then dust appears slowly at various scales, starting to impact, I guess, star formation, galaxy formation, you name it. Can you maybe comment on that?
Yeah, so as I mentioned earlier, just briefly, the growth rates, formally there's no threshold metallicity where the instability appears. Some of the specific subversions do have one. So famously, the people talk about the streaming instability having a threshold metallicity, but actually, that if you really want to get technical, there's technically two instabilities that are part of the streaming instability, and one of them has a threshold metallicity, one of them doesn't. But a version of this instability will appear at basically any metallicity, and in fact, the dependence of the growth rate on metallicity can be highly sublinear, as low as metallicity or dust to gas ratio, really, as low as dust to gas ratio to the 1/3 or 1/4 power, depending on which instability it is. So that's a pretty weak dependence. But of course, at some point, as you say, metallicity or dust to gas ratio goes to 0, so that still goes to 0, basically. So it is really interesting to think about what's happening there, and wildly speculatively, with Charlie Conroy a couple of years ago, we sort of made some very order of magnitude estimates of, if you imagine a very weakly polluted ISM, like metallicity of 10 to the -4 or 10 to the -5 or something, of -4, -5, even there, it could be very interesting for the following reason. Even though the metallicity is very low, as you probably know, working on early universe and EOR, there's a lot of speculation that for the first second generation stars, the first dwarf stars, even a very small amount of dust might play a crucial role in the cooling physics to allow them to cool enough to fragment to dwarf star scales, basically. So what we were wondering about is, even if you have a tiny amount of dust, if these instabilities can operate and concentrate that dust, it could be crucial. It could dominate the formation of those second generation stars, basically, because of its effect on the cooling and because there's not many other cooling channels around, basically. So that's very hand wavy and just a guess about what's worth exploring there. It's going to depend on the details of actually how quickly this growth rate, at some metallicity that's low enough, or some dust to gas ratio that's low enough, the growth rates, even if they're sublinear, will get so long that it can't be interesting compared to other dynamical timescales of the system. But it's not. But just doing it back of the envelope for star formation timescales in high redshift protogalaxies, anybody who knows anything about this field knows I've just inserted theoretically like 10 different twiddles in that series of statements. It's not clearly unimportant. It's very much in the range, in the mix that could be important there. So maybe I think a fascinating thing would be to look at sort of that second generation star formation after a first POP3 supernova or something, right? Seeing what it would do to the ejecta and the dust in that ambient medium. Yeah.
All right, so I think we're out of time because Phil, you have meeting with our grad students, and there are some messages of appreciation of the talk and the beautiful images as well. So I encourage you to look at the chat. And otherwise, thank you so much again for the very nice talk.
Thank you all. Really, happy to be here and happy to hear you all, have you all hear me talk about dust and give me an excuse to show pretty pictures. And look forward to talking more in the future with many of you. Cheers.
Yeah. Have a good day, everyone.
Yeah.